The next thing we're going to talk about is something that comes up again as we discuss climate change, and that has to do with sea level, right? So not sea surface temperature, we just got through, but sea level itself. And one of the things we often talk about is sea level rise. And so what the heck is sea level, right? So what is zero? And it turns out that's a big question, right? So there's a lot of different variables. So things that can affect the sea level really kind of on the short term, and the definition of short term, we're kind of thinking in days is tides, or we have tides that come through. We've got wind, which is kind of blowing the water around, or kind of sustained winds in direction can kind of pile water up in a certain area, affecting sea level. Salinity, right? So salt in the water takes up volume. So with increased salinity comes increased volume. If you took a jar of water and you poured a whole bunch of salt in it, the water level would rise. Temperature also can affect that. And this can change seasonally or also kind of on longer time scales. And so as the thermal mass of the ocean changes, warmer water takes up more space than cooler water. Before I had kids, I was a really prolific home brewer, and I would fill my my hot water tank up to 15 gallons even with water from the tap. Came out, 54, 55 degrees, and I would heat that water up to 170 degrees. And at that point, the water had grown from 15 gallons to 15 and a half gallons. So increased thermal mass, the water can actually grow and shrink. And that happens on seasonal scales, right? So the sea surface temperature changes over the course of 1 year, which means the volume changes over the course of 1 year. So how do we solve all of this, right? How do we cancel this out? Well, we really do it with statistics, right? So we could have a station. You can see here I drew a coastal area. Let's say we've got buildings, land up here. We've got a pier that we could go out onto, and we could have a station that's gonna measure our sea surface. And so we could do this, like I said, in a couple of different ways. We could actually stick a device down that has essentially a buoy in an enclosed tube. And what that would do is basically like sticking a ruler into the water. The enclosed tube, if it's open at the bottom so water can flow in, I guess I forgot to include that part of my diagram, the water will sit fairly stable, just like the water level in your straw. If you put it in your soda, right? Your soda's filled with ice. And if you shake your soda around, the water will slosh in your drink, but not very much in the straw. And then to solve for mean sea level at this observation location, this is what we would call like a tidal observation station, we could look every hour and mark the level of the water. Right, so tides are going to go up, tides are going to come down, storms are going to come in, storms are going to come out. If we took 20 years of data and we had hourly measurements of sea level, we could actually just average that, right? And that would be our definition of sea level. So it's not necessarily like there's anything that you could just point to and say, this is the definition of sea level. You have to collect a lot of data, compile that data over a number of years, and that could be your sea level. So again, using this with a ruler and a gauge that's going to kind of keep track, and if this is manual, you can't do it every couple of minutes. Kind of in the olden days, maybe every hour you would check. We've gotten away from that, right? So that has a lot of human error that could be built into the system. So in the kind of near modern way, we have, again, a tube that would go down, but then we have a device at the top that sends essentially a sonic wave or a kind of pulse of energy down, and that energy then reflects off of the water. So we have a device up here that's a sonic device, and it sends a little pulse of sound down, and like a kind of echolocation, right, in a way that bats would navigate a cave or something like that. And that would bounce back off of the water. It would give us a depth. And so in that case, that's kind of been our standard for quite a long time. We're in the process of moving away from that. So again, that's pretty accurate. These devices generally check the water level every 6 minutes. And then every so often we actually come and do a ground check, like a human check. But every 6 minutes we have a different reading for a sea level at that location. That's pretty cool, right? So that takes some of the workload out, but there are some problems, right? So we've got a sensor that needs to be kind of kept track of. It needs to be calibrated. We need to make sure that it's measuring the right thing, and also there's portions that could be in the ocean, right? And then at that point, maybe they get covered with sea creatures or barnacles, those sorts of things. And you would have to actually go down and manually clean these things off from time to time. So that's what we've used, and that's actually what we use currently at hundreds and hundreds of tidal observation stations around the world, because it's technology that works. But actually, what we're currently doing is we're moving away from that, and we have a device that actually sticks kind of out over the water and sends a kind of microwave pulse down to the surface of water, and that in a very similar way to what we saw before, although that was an acoustic tube, right? It was sending a sound pulse, essentially an echo. And in this case, we can send microwaves down, and they reflect back, and we can get depth. So the advantages of this are that there's no parts that are in the water. But switching from one mode of instrumentation to another obviously can introduce some difficulties. So you can see that this is a tidal observation station, a NOAA station outside of San Francisco. I believe it's been there for about 150 years, but the instrumentation has changed over time, right? And so again, initially it was essentially a ruler, and then we moved away from rulers and got to sonic pulse. And then now we're doing these kind of microwave, these microwave reflection times, right, to find the distance down to the water. So that's all kind of ground truth, right? And this is obviously only possible in places that we can access, right? Coastal areas, places where you can put in a pier and go out and do this sort of research. One of the things that we kind of think about beyond this is, well, how can you measure sea level without being there, right? And so this is what we call data that's remotely sensed, right? That's a term that kind of comes up in geology, geography, climatology a lot, remote sensing. And that's to collect data without actually going there. Oftentimes, remote sense data is either collected by an airplane, drones in the modern world, or satellites, right? And so sea level, we actually measure really since the 1990s with satellite altimeters, meaning they can actually measure, again, in a very similar way, the distance in a kind of highly precise way to the water. But just as with other things, that requires ground truth, right? So if there's problems with your remote sense data, you're going to need to have kind of a solid observation where someone or some device actually took that measurement. And when we think about stripping away, some of the short-term changes, we start to think about things that can change sea level in the longer term and in the kind of medium term, right? The kind of mid-range sea level changes. So we talked about, seasonality, water temperature fluctuations over the course of the year. And with long enough records, we can actually recognize those patterns and we can eliminate those mathematically from the data, which is really pretty cool. But what does change sea level? So, like I said, there's things that happen in the short term, storms and such. There's also things that can happen in the very long term, right? Like continents moving around. There's kind of vertical, what we call isostatic movements of continents that change the shapes of ocean basins. That's obviously a sea level change that's much kind of longer scale than we're interested in this case. But really the ones that we're going to be focusing on is the thermal mass, right? Remember we talked about the ocean heat content, or the OHC. That's the amount of energy stored in the oceans. Well, that changes from year to year, but it also changes overall as more and more and more and more heat is stored in the oceans. And so we've seen, we have, getting close to 150 years of data from these tidal observation stations, the sea level is slowly rising, on the order of millimeters per year. This is data that NOAA has, and we can see very clearly, this kind of slow sea level rise that's, again, overprinted by these kind of seasonality changes. So what can cause that? Again, we talked about the heat mass in the ocean itself. And then on top of that, we can actually think about adding water to the oceans in a bulk sense, right? Adding water to the oceans that wasn't there in a previous time. So the number one source for that is actually glaciers, right? So if we think about a place like an ice cap, Antarctica, the thickest ice in the Antarctica is, close to 3 miles thick. I think the thickest ice in Antarctica is 1,400 feet thick. That's a lot of ice. And that ice is water, and it's stored on the continents, right? And so as that ice is to melt, that water shifts from being stored in a kind of frozen reservoir on a continent to in the ocean basin. So in the modern world, when we look at sea level rise, again, we can look at these graphs and see how much sea level has changed over the last 100 years or so. Roughly 3/4 of that has to do with thermal expansion of the water, again, tied to ocean heat content, and about 1/4 of that is supplied by melting glaciers, so water that's previously stored on the continents. So hopefully, at the end of this, you can see really the care and the precision that's taken in measuring at least 3 of the variables that we've talked about this week. So air temperature over the continents and different ways that we measure that, sea surface temperature, both at depth and skin, and sea level rise. And another thing that's obviously really apparent in all of those is kind of the evolution of technology, right? So we've gotten to the point where we can detect, sea level rise with millimeter precision, changes in sea surface temperature by fractions of a degree, and our temperature record on the continents is incredibly robust and getting longer and longer and longer each year. And there's more and more and more weather stations. And so kind of compiling all of this, we can really start to get a complete picture of the atmosphere today, like a snapshot, what all of those conditions are today. And the kind of time record of that continually evolves, right? So we can see how that's changed, over the past 100 years. Remember, we talked about the instrumental temperature record really goes back to kind of about the 1880s. So all of those show kind of what we would expect, right? We've got rising temperatures on the continents. No surprise there. We've got rising sea surface temperatures. Again, no surprise there. We have rising sea levels, and all of those are incredibly rigorously documented. Okay, well, that's going to do it for our measurement bits, and I will go ahead and see you next time. All right, bye.